Dear students, welcome to another video lecture on the course Signals and Systems with course code 18EC45. In the last video lecture, we did solve some problems on discrete time Fourier transform and understood the nature of its spectrum. Discrete time Fourier transform's spectrum is continuous and periodic with respect to 2 pi period. And from DTFT's spectrum, we can draw magnitude spectrum and phase spectrum separately. Magnitude as well as phase spectrum will also be continuous and periodic with respect to 2 pi period. But magnitude spectrum of DTFT will always be an even function and phase spectrum will always be an odd function. In today's lecture, we'll be starting our discussion on properties of discrete time Fourier transform. The first property we'll be studying is linearity. For any physical quantity or entity to be linear, it should satisfy the principle of homogeneity and superposition. Linearity in context with Fourier transform is defined as if x of n and x of omega are the discrete time Fourier transform pair. It means if we have x of n, by forward transform, the spectrum x of omega can be obtained, and if we know the spectrum x of omega, then by inverse transform, discrete time signal x of n can be obtained back. So transform pair will be represented by a two-sided arrow with the superscript DTFT written over it. And if we consider another signal y of n and its transform pair y of omega, then if we form a composite signal z of n by adding x of n and y of n, addition of x of n and y of n is nothing but the superposition. Multiplication of the constants a and b to the signals x and y is the homogeneity. Then the transform should also satisfy the principle of homogeneity and superposition. According to linearity, if we form a composite signal by adding x and y, then their corresponding spectrums x of omega and y of omega will also be superimposed and multiplied by the respective constants. So according to linearity, the composite signal z of n defined as ax of n plus by of n should result into the spectrum z of omega, which is defined as ax of omega plus by of omega. To prove linearity, we'll start with the definition of discrete time Fourier transform. Only the variable has been changed to z instead of x. The overall definition is same. Z of omega equals to summation n minus infinity to plus infinity discrete time sequence z of n e to the power minus j omega into n. In place of z of n, we'll substitute the composite signal ax of n plus by of n. Summation is also linear, so it can be split between two terms, and constants a and b are independent of these summations, so they can be taken out. So rewriting the summations, we'll get a times summation n minus infinity to plus infinity x of n e to the power minus j omega n plus b times summation n minus infinity to plus infinity y of n e to the power minus j omega into n. Now if you observe both the summations, They are the standard definitions of discrete time Fourier transform. So the first summation can be written as x of omega, which is the spectrum for the sequence x of n, and second summation can be written as y of omega, which is the spectrum for the sequence y of n. So the proof for the linearity is z of omega is equal to a x of omega plus b y of omega, which is the required proof for linearity. The second property we'll be studying is time shift, or sometimes it is also referred to as time translation. And the statement for time shift property is, if x of n and x of omega are the transform pair, and if you shift the discrete time sequence x of n by n naught samples, which is represented by x of n minus n naught, this time shifted sequence is denoted by y of n. Then the effect of this time shifting on the frequency domain signal or on the spectrum x of omega will be multiplied by a discrete sinusoidal signal of frequency n naught into omega. So spectrum y of omega will be e to the power minus j omega into n naught x of omega, where n naught corresponds to the time shift of the signal. Again, to prove this, we'll start with the definition of Fourier transform. Y of omega equals to summation n minus infinity to plus infinity y of n e to the power minus j omega into n. In place of y of n, we'll use the time shifted signal x of n minus n naught e to the power minus j omega into n. In place of n minus n naught, we will substitute the variable m. So the variable on the summation will change to m, x of m e to the power minus j into omega, and in place of n, we'll be using m plus n naught. If you decompose this exponential, we'll be having two parts. One of the exponential will be e to the power minus j omega into n naught, which is independent of the summation, so it can be taken out. And another exponential along with the remaining terms in the summation, e to the power minus j omega m x of m summation m minus infinity to plus infinity, is the standard discrete time Fourier transform definition. So the spectrum y of omega will be e to the power minus j omega into n x of omega. The spectrum will be multiplied by a discrete time sinusoidal signal with frequency n naught into omega, where n naught corresponds to the time shift of the discrete time signal. The third property we'll be studying is frequency shift, or sometimes it is also referred to as frequency translation. Again, if x of n and x of omega are the transform pair, and this time if the spectrum x of omega is shifted to beta frequency represented by x of omega minus beta, and if this if this frequency shifted spectrum is represented by y of omega, then its effect on the time domain signal will be the discrete time signal x of n will be multiplied by a discrete sinusoidal signal with frequency beta into n, where beta corresponds to the frequency shift of the spectrum. To prove this, we'll start with Fourier transform definition again. Y of omega equals to summation n minus infinity to plus infinity y of n e to the power minus j omega into n. In place of y of n, we'll substitute the time domain signal e to the power j beta into n multiplied by x of n. We can combine both the exponentials inside the summation and rewrite it as summation n minus infinity to plus infinity x of n e to the power minus j omega minus beta of n. So this is the definition of the Fourier transform for the frequency omega minus beta. So the spectrum y of omega is x of omega minus beta. The next property we'll be studying is scaling. Scaling here refers to time scaling. Time scaling property of discrete time Fourier transform is somewhat different compared to time scaling property of continuous time Fourier transform. So to elaborate, let us consider the time scaling property of continuous time Fourier transform. If x of t is a continuous time signal, then xa of t is the time scaled version of that continuous time signal x of t, and its continuous time Fourier transform spectrum is defined as 1 divided by mod of a x of j omega divided by a. This is the property for continuous time Fourier transform for scaling. But for this to be possible in discrete times case, a should be an integer always. If a is not an integer, then x of a into n will no longer be a sequence altogether, because discrete time signal is defined only at integer values. For example, if a is equal to 4, then x of 4 into n will consist only even samples of the x of n. This means we'll be having loss of samples, loss of information in the time scaled sequence of in discrete time. So to accommodate this, let us define a to be a positive integer and define the time scaled signal as xa of n to be represented by x of n divided by a, where a is the scaling factor, which can in turn be equated or represented by x of k. If n is equal to k into a, and the condition is k and a both should be integers, and the sequence will be 0 if n is not equal to k into a, then the statement, time scaling properties statement, will be defined as if the discrete time sequence is time scaled, then the spectrum will also be scaled by the same factor. So the property is given as xa of n's dtft will be represented by capital X of a into omega, where a is the scaling factor. To prove this, we'll consider the definition of discrete time Fourier transform again. Xa of omega equals to summation n minus infinity to plus infinity xa of n e to the power minus j omega into n. In place of time scaled version of the discrete time signal, we'll substitute x of n divided by a. If we substitute n divided by a as m, then n will be equal to m into a. We'll use these results in the above summation. So the spectrum xa of omega will be equals to summation m minus infinity to plus infinity x of m e to the power minus j omega m times a. If you combine omega and a in the exponential, then the spectrum can be represented by x of a into omega. So if you perform time scaling for a discrete time sequence, then spectrum will also be scaled by the same quantity. And the last property we'll be studying for the day is frequency differentiation. The statement of frequency differentiation is if x of n and x of omega are transform pair, and if you differentiate the frequency domain signal, that is x of omega, and represent it as dx of omega divided by d omega, differentiation is with respect to omega, then the time domain signal x of n will be multiplied by the quantity minus j into n. To prove this, we'll start with the definition of discrete time Fourier transform and differentiate both the sides with respect to omega. Dx of omega divided by d omega equals to summation n minus infinity to plus infinity. Differentiation is with respect to omega, so x of n is written as it is, and the differentiation of the exponential e to the power minus j omega n is minus j into n e to the power minus j omega into n. So if you combine x of n and minus j into n, or if you look at it together, then the summation is the standard discrete time Fourier transform of the sequence x of n minus j into n. So minus j into n x of n's discrete time Fourier transform will be the first derivative of the spectrum. I hope you all understood all the 5 properties. If you have any doubts, you can contact me on my email or my personal number. Thank you all.